On the evening of April 10th, 2019, in a conference room at the National Science Foundation in Washington, D.C., a young woman named Katie Booman sat in front of a laptop, her hands covering her mouth. On the screen was an image, orange and asymmetric, a glowing ring of superheated gas surrounding a dark void roughly the size of our entire solar system. She was looking at something that no human being had ever seen before. She was looking at a black hole, not an artist's rendering, not a computer simulation, not a theoretical prediction sketched on a whiteboard, an actual photograph of an actual black hole 55 million light-years away, at the heart of a galaxy called Messier 87, captured by a telescope the size of the Earth. The image had taken 2 years to process. The data it was built from weighed half a ton, literally, physically. Half a ton of hard drives that had to be shipped by cargo plane from observatories on 4 continents because no internet connection on Earth was fast enough to transmit the volume of information they contained. The computational challenge of assembling those petabytes of radio data into a single coherent picture had required entirely new algorithms, and Booman had helped write them. When the image finally resolved on her screen, she gasped. Not because it was surprising, the theorists had predicted almost exactly what it would look like, but because it was real. A century after Einstein's general theory of relativity first predicted that objects of sufficient mass would warp space-time so severely that nothing, not even light, could escape their gravitational pull. Humanity had proof. The darkness at the center of that glowing ring was the event horizon, the boundary beyond which information ceases to exist, where time itself, according to our best understanding of physics, simply stops. But here's the part of the story that almost nobody talks about, and it is in many ways more remarkable than the image itself. The telescope that captured it does not exist. There is no single instrument called the Event Horizon Telescope. There is no dish, no mirror, no lens. What exists is a collaboration, a network of 8 radio observatories scattered across the planet, from the volcanic summit of Mauna Kea in Hawaii to the frozen plateau of the South Pole, from the high desert of Chile's Atacama to the pine forests of southern Spain. Each of these observatories is an independent facility with its own staff, its own funding, its own research agenda. Separately, none of them could have captured the black hole image. The angular size of M87's event horizon, as seen from Earth, is roughly 42 micro-arcseconds, about the size of an orange on the surface of the Moon if you were standing in New York. To resolve something that small at radio wavelengths, you would need a dish antenna approximately 13,000 kilometers in diameter, the diameter of the Earth. The trick, and it is one of the most elegant tricks in all of observational science, is a technique called very long baseline interferometry. You do not need a single dish the size of the Earth. You need multiple dishes separated by Earth-sized distances, all observing the same target at the same time, with their data meticulously synchronized using atomic clocks accurate to within a trillionth of a second. Each pair of telescopes captures a slightly different piece of the spatial information contained in the incoming radio waves. By combining all the pieces, a computer can reconstruct what a single Earth-sized dish would have seen. The concept is simple. The execution is nightmarish. Every observatory in the network had to be equipped with hydrogen maser atomic clocks, the most stable timekeeping devices ever built, because the synchronization had to be maintained to within a few picoseconds across distances of thousands of kilometers. The observations had to be made simultaneously, which meant that the weather had to cooperate at all 8 sites at the same time, a condition that, given the geographic spread from the Atacama Desert to the South Pole, was about as likely as winning the lottery. Data rates were so high that no existing network could handle the transmission in real time. So the raw data was recorded on banks of helium-filled hard drives, the half-ton shipment I mentioned, and physically transported to correlator facilities in Massachusetts and Germany. The South Pole data, recorded during the Antarctic winter, could not be shipped out until the following October, when the first supply flights of the season arrived. For months, The entire collaboration waited, unable to complete their analysis, while hard drives containing irreplaceable observations sat in a storage room at the bottom of the world. The observation window in April 2017 lasted just 5 nights. April 5th, 6th and 7th produced usable data. April 8th and 9th were lost to high winds at the Mexican and Arizona sites. April 10th and 11th added the final observations. 5 nights. 5 nights to capture an image that would take 2 years to process and would confirm one of the most profound predictions in the history of physics. When the image was finally released, it matched the theoretical predictions with eerie precision. General relativity had told physicists exactly what a black hole should look like. The dark central shadow, the bright photon ring, the asymmetric brightening caused by the Doppler effect as matter in the accretion disk rushed toward and away from the observer at significant fractions of the speed of light. Computer simulations produced by NASA years before the observation showed almost exactly what the EHT eventually captured. Einstein, working with nothing but pencil and paper in 1915, had gotten it right. The black hole at the center of M87 is a monster. Its mass is 6.6 billion times that of our Sun. Its event horizon spans roughly 38 billion kilometers, large enough to swallow our entire solar system with room to spare. Matter spiraling into it forms an accretion disk heated to billions of degrees, and along the axis of rotation, jets of ionized plasma are ejected at nearly the speed of light, extending outward for thousands of light years. The Hubble Space Telescope had photographed one of these jets years earlier, a luminous spike of matter shooting out from the galaxy's core like a cosmic blowtorch. But only the EHT could reveal the engine driving it, the shadow of the event horizon itself, the point of no return. The team is not finished. Plans are already underway to add more telescopes to the network, improving resolution and enabling something that was unthinkable just a decade ago: movies. Not still images, but time-resolved sequences showing how the accretion disk churns and roils, how magnetic field lines twist and snap, how space-time itself behaves in the most extreme gravitational environment in the observable universe. There are also plans to image the black hole at the center of our own galaxy, Sagittarius A-star, which is much closer, only 26,000 light-years away, but much smaller and more variable, flickering and changing on timescales of minutes rather than days. The existence of that black hole, Sagittarius A-star, the dark heart of the Milky Way, was established not by the EHT, but by a different group of astronomers using a different technique, and their story is almost as remarkable. In 1992, a team from the Max Planck Institute for Extraterrestrial Physics began a program of observations at the European Southern Observatory's New Technology Telescope at La Silla, Chile. Their target was the center of our galaxy, a region so dense with gas and dust that it is completely invisible in optical light. You cannot see the galactic center with your eyes, no matter how powerful your telescope, but infrared light, heat radiation essentially, can penetrate the obscuring clouds, and the NTT was equipped with infrared detectors sensitive enough to pick out individual stars in the crowded central region. Over the following years, using progressively larger telescopes as they became available, first the NTT, then the giant 8.2-meter instruments of the Very Large Telescope at Paranal, the team painstakingly tracked the positions of 28 stars in the galactic center. Year after year, they recorded the stars' positions with extraordinary precision, building up a map of their trajectories. What they found was astonishing. The stars were not drifting randomly. They were orbiting something invisible, something enormously massive, something that occupied a volume of space smaller than our solar system. One star in particular told the story with devastating clarity, designated S2. It traces a highly elliptical orbit around the invisible object, completing one lap every 16 years. At its closest approach, a moment called periapsis, S2 passes within about 17 light hours of the unseen mass, screaming along at roughly 3% of the speed of light, about 7,650 kilometers per second. From the shape and speed of S2's orbit, the team calculated the mass of the invisible object, approximately 4.1 million times the mass of our Sun, compressed into a region smaller than the orbit of Mercury. There is only one thing it can be: a supermassive black hole. In May 2018, S2 reached its closest approach, and the team was ready. General relativity makes a specific prediction about what should happen to light emitted by an object moving that fast in a gravitational field that strong. The light should be shifted toward the red end of the spectrum, a phenomenon called gravitational redshift. The team measured it. The shift was there, precisely as Einstein had predicted. Another vindication for a theory that is now more than a century old and has never once been found wanting. The observations of S2 matter for a reason that goes beyond confirming Einstein. General relativity predicts that inside a black hole's event horizon, the normal rules of physics cease to apply. Time and space swap roles. Causality becomes meaningless. The singularity at the center, a point of theoretically infinite density, represents a genuine breakdown of our understanding of nature. By studying the behavior of matter and light in the extreme gravitational environment just outside the event horizon, physicists hope to find cracks in general relativity, places where the theory begins to fail, pointing the way toward a deeper, more complete description of the universe. So far, Einstein's equations have held up perfectly, but the search for their limits continues, and the galactic center is the most extreme laboratory available. The telescopes that made these observations possible represent a revolution in how we see the universe, and that revolution is worth understanding because it touches everything from black holes to exoplanets to the fate of life on Earth. For centuries, the history of astronomy was essentially the history of building bigger mirrors. The logic was straightforward. A larger mirror collects more light, which means you can see fainter and more distant objects. But by the late 20th century, the approach had hit a wall. A conventional telescope mirror, much larger than about 8 meters in diameter, becomes so heavy that it sags under its own weight. As the telescope swings to point at different parts of the sky, gravity distorts the mirror's precise curvature by tiny but fatal amounts, blurring the image. The Hale telescope on Palomar Mountain, with its 5.1 meter mirror, had defined the cutting edge for decades, but scaling up further with a single rigid piece of glass was physically impossible. Two innovations broke through this barrier. The first was the segmented mirror. Instead of casting one enormous piece of glass, you build the mirror from an array of smaller hexagonal segments, each one individually controllable, each one adjusted in real time by computer-driven actuators that monitor the mirror's shape hundreds of times per second and correct for gravitational distortion. This is called active optics, and it was first deployed at the twin Keck telescopes on Mauna Kea, Hawaii, each of which has a 10-meter mirror assembled from 36 hexagonal segments. The system works beautifully. The segments move by amounts measured in nanometers, billionths of a meter, keeping the mirror's surface accurate to a fraction of a wavelength of light. The second innovation is adaptive optics, and it solves an entirely different problem. Even a perfect mirror on a perfect night cannot overcome the fundamental limitation of ground-based astronomy. The atmosphere, the air above a telescope, is never still. Temperature variations create pockets of slightly different density, and light passing through these pockets is refracted, bent by tiny, rapidly changing amounts. The result is the twinkling of stars, which is charming to poets and catastrophic to astronomers. A star that should appear as a sharp point is instead smeared into a fuzzy blob several times larger than the telescope's theoretical resolution. Adaptive optics attacks this problem head-on. A wavefront sensor monitors the light from a bright reference star, or if no suitable natural star is available, an artificial one created by shining a powerful laser into the upper atmosphere, where it excites sodium atoms at an altitude of about 90 kilometers, producing a glowing dot that serves as a calibration source. The sensor measures how the atmosphere has distorted the incoming light, and a deformable mirror, a thin, flexible surface behind the main mirror, adjusts its shape hundreds or even thousands of times per second to cancel out the distortion. The correction is never perfect, but it is dramatic. Images taken with adaptive optics from the ground now rival or exceed the sharpness of images from space. A photograph of Jupiter taken with the Keck telescope's adaptive optics system is essentially indistinguishable from one taken by the Hubble Space Telescope. These technologies have not merely improved our existing telescopes, they have made possible an entirely new generation of instruments that would have been inconceivable a few decades ago. The European Southern Observatory is building the extremely large telescope in Chile's Atacama Desert with a primary mirror 39 meters in diameter, assembled from 798 hexagonal segments that will collect more light than all existing large telescopes combined. When it begins operations in the late 2020s, it will be able to directly image exoplanets orbiting nearby stars and analyze the composition of their atmospheres, searching for chemical signatures of life. The Atacama Desert is one of the driest places on Earth. Some parts of it have not received measurable rainfall in recorded history. The air is thin, dry, and extraordinarily transparent, ideal conditions for astronomy, which is why the European Southern Observatory has concentrated its facilities there. At the Paranal Observatory, 4 identical 8.2-meter telescopes, collectively called the Very Large Telescope, can operate independently or linked together using interferometry, combining their light to achieve the angular resolution of a telescope with a mirror the size of the distance between them. At the Chajnantor Plateau, 5,000 meters above sea level, 66 radio dishes form the Atacama Large Millimeter Array, or ALMA, observing at wavelengths between infrared and radio. These frequencies penetrate the gas and dust clouds that block visible light, revealing the hidden interior structures of stellar nurseries, protoplanetary disks, and distant galaxies. Telescopes in space remain important because certain wavelengths, ultraviolet, X-ray, gamma ray, and parts of the infrared, are absorbed by the atmosphere and can never reach the ground. The Hubble Space Telescope, launched in 1990, has been the most scientifically productive and publicly beloved space telescope in history. Its story is both a triumph and a cautionary tale, and it reveals something fundamental about the nature of scientific enterprise, that the greatest discoveries often emerge from the most painful failures. When Hubble was deployed from the cargo bay of the Space Shuttle Discovery on April 25, 1990, expectations were enormous. The telescope's 2.4-meter primary mirror had been ground to what was believed to be the most precise optical surface ever manufactured, accurate to within 10 nanometers, roughly 1/50th the wavelength of visible light, free from atmospheric distortion. Hubble was expected to deliver images of unprecedented sharpness, opening a new window on the universe. The first images were devastating. They were blurred. Not slightly blurred, obviously, unmistakably blurred. Stars that should have been sharp points were surrounded by fuzzy halos. The telescope's resolution was no better than a good ground-based instrument. Something was badly wrong with the mirror. The investigation that followed revealed a manufacturing error so small in physical terms and so enormous in its consequences that it became a case study in quality control failures. The primary mirror had been ground with exquisite precision but to the wrong shape. The curvature was off by about 2.2 micrometers, roughly 1/50th the thickness of a human hair. This tiny error had been introduced by a flaw in the testing instrument used to verify the mirror's shape during manufacturing. A small lens in the instrument had been positioned incorrectly by 1.3 millimeters. This caused the instrument to report that the mirror was perfect when it was not, and no one had performed an independent check. The The error was devastating, but because it was precise, a known, measured, consistent distortion, it was also correctable. Engineers designed a device called CoStar, essentially a set of small corrective mirrors that would be installed inside the telescope to compensate for the primary mirror's flaw. It was in effect a pair of glasses for a nearsighted telescope. The repair mission launched in December 1993 aboard the Space Shuttle Endeavour. Over 5 spacewalks, spanning 11 days, astronauts installed CoStar, replaced the original wide-field camera with an upgraded version that had its own built-in corrective optics, swapped out the solar panels, replaced electronic processors and gyroscopes, and performed a long list of other maintenance tasks. It was the most complex orbital servicing operation ever attempted, and it went flawlessly. When the corrected telescope delivered its first images, the transformation was breathtaking. Stars were needle-sharp, galaxies resolved into individual components, spiral arms, dust lanes, star-forming regions, with a clarity that no telescope had ever achieved. The astronomical community, which had spent 3 years mourning what seemed like a billion-dollar boondoggle, suddenly found itself in possession of the most powerful observational tool in history. What followed was a quarter-century of discoveries that reshaped our understanding of the cosmos. In 1994, Hubble watched as the fragments of comet Shoemaker-Levy 9 slammed into Jupiter, producing dark impact scars the size of the Earth that persisted in Jupiter's atmosphere for months. Spectral analysis of the impact sites revealed chemicals, diatomic sulfur, carbon disulfide, that had never been detected at Jupiter before. They had been dredged up from deep within the planet's interior by the force of the collisions, giving scientists their first glimpse of Jupiter's hidden composition. In 1995, astronomers pointed Hubble at a tiny, apparently empty patch of sky near the constellation Ursa Major. They left it staring at that patch for 10 consecutive days, collecting light. The idea seemed almost wasteful. Why spend 10 days of precious Hubble time looking at nothing? The result was the Hubble Deep Field, one of the most famous images in the history of science. The empty patch of sky turned out to be packed with galaxies, roughly 3,000 of them, in a region of the sky that you could cover with a grain of sand held at arm's length. Some of the galaxies were irregular, distorted, clearly still in the process of forming. Their light had been traveling for more than 12 billion years, meaning Hubble was seeing them as they existed when the universe was less than 1 billion years old. It was a direct window into the epoch of galaxy formation, and it revealed that the early universe was a far more chaotic and violent place than anyone had imagined. Subsequent deep field observations, the Hubble Deep Field South, the Ultra Deep Field, the Extreme Deep Field, pushed even further, detecting galaxies whose light had been traveling for more than 13 billion years, approaching the theoretical limit of what Hubble could see. Beyond that limit, the expansion of the universe has stretched the light from the earliest galaxies so far into the infrared that Hubble's detectors, optimized for visible and near ultraviolet wavelengths, can no longer detect it. To see further, to see the very first galaxies, the first stars, the moment when the universe emerged from the cosmic dark ages, would require a different kind of telescope. A bigger telescope, a colder telescope, an infrared telescope. That telescope is the James Webb Space Telescope, and it represents perhaps the most ambitious engineering project in the history of science. Its primary mirror is 6.5 meters in diameter, nearly 3 times the collecting area of Hubble's, assembled from 18 hexagonal segments of gold-coated beryllium. The entire structure is so large that it could not fit inside any existing rocket fairing in its deployed configuration. It had to be designed to fold, origami style, into a compact package for launch, and then unfurl itself over a period of weeks after reaching its destination. That destination is not low Earth orbit, where Hubble resides. Webb orbits the Sun at the second Lagrange point, or L2, a gravitationally stable location about 1.5 million kilometers from Earth, on the side away from the Sun. At L2, the Earth, Sun, and Moon are all on the same side of the telescope, which means a single sun shield can block all three sources of heat and light simultaneously. The sun shield, a 5-layered membrane of aluminized kapton, each layer thinner than a human hair, is about the size of a tennis court, and it reduces the temperature on the telescope side to about 50 Kelvin, minus 223 degrees Celsius. The mid-infrared instrument requires even colder conditions and is equipped with a mechanical cooler that chills its detector to just 7 Kelvin, barely above absolute zero. These extreme temperatures are necessary because Webb is designed to see in the infrared, and any source of heat, including the telescope itself, would overwhelm the faint signals from distant galaxies. At 50 Kelvin, the telescope's own thermal emission is negligible, and the detectors can register photons that have been traveling across the universe for more than 13 billion years, stretched by the expansion of space from their original ultraviolet and visible wavelengths deep into the infrared. Webb launched on Christmas Day 2021 aboard an Ariane 5 rocket from the European spaceport in Kourou, French Guiana. The deployment sequence, sun shield, mirror segments, secondary mirror, instrument booms, took 2 weeks and involved more than 300 single point of failure mechanisms, any one of which, had it malfunctioned, could have ended the mission. Every single one worked perfectly. The first full-color images, released in July 2022, showed galaxy clusters, stellar nurseries, and exoplanet atmospheres with a depth and clarity that even the most optimistic scientists had not dared to expect. But the search for worlds beyond our own solar system, one of Webb's primary scientific objectives, did not begin with Webb. It began decades earlier with a revolution in detection techniques that transformed exoplanet science from speculation into one of the fastest growing fields in all of astronomy. For most of human history, the existence of planets around other stars was a matter of philosophical conjecture. Epicurus argued for it in the 3rd century BCE. Giordano Bruno was burned at the stake in 1600 partly for insisting on it. But there was no evidence because exoplanets are fantastically difficult to observe directly. A planet does not produce its own light. It shines only by reflecting the light of its parent star, and that reflected light is roughly 1 billion times fainter than the star itself. Trying to see an exoplanet next to its star is like trying to spot a firefly hovering next to a searchlight from 1,000 kilometers away. The breakthrough came from an indirect approach. Instead of trying to see the planet, you look for its effect on the star. A planet does not simply orbit a star, the star and planet orbit their common center of mass. For a massive planet like Jupiter, this causes the star to wobble, a tiny periodic back and forth motion that can be detected as a shift in the star's spectral lines. When the star moves toward you, its light is compressed to slightly shorter wavelengths, a blue shift. When it moves away, the light is stretched to slightly longer wavelengths, a red shift. By measuring these shifts with a high-precision spectrograph, you can infer the presence of a planet, estimate its mass, and determine its orbital period. This is the radial velocity method, and in 1995 it produced the first confirmed detection of an exoplanet around a Sun-like star, 51 Pegasi b, a gas giant, roughly half the mass of Jupiter, orbiting its star in just 4.2 days. The discovery was shocking. Not because an exoplanet had been found, most astronomers expected they existed, but because of where it was. A Jupiter-mass planet in a 4.2-day orbit is unimaginably close to its star, far closer than Mercury is to our Sun. The surface temperature would be well over 1,000 degrees Celsius. Nothing in our solar system resembled it. Theorists scrambled to explain how such an object, soon dubbed a hot Jupiter, could exist, and their efforts led to a complete reimagining of how planetary systems form and evolve. The second major detection method is the transit method. If a planet's orbit is aligned so that it passes between its star and the Earth, it will block a tiny fraction of the star's light, a dip in brightness that repeats with every orbit. The depth of the dip tells you the planet's size. The timing tells you its orbital period. If you also have radial velocity data, you can calculate both the mass and the radius, giving you the density, which in turn tells you whether the planet is rocky, gaseous, or something in between. The transit method is exquisitely sensitive to the right kind of planet, one whose orbit happens to be edge-on to our line of sight, but it misses the vast majority of planets whose orbits are tilted at other angles. Nevertheless, it has been spectacularly productive, largely because it lends itself to automated, wide-field surveys that can monitor millions of stars simultaneously. The Kepler Space Telescope, launched in 2009, stared at a single patch of sky for 4 years, monitoring the brightness of more than 150,000 stars, and discovered more than 2,600 confirmed exoplanets. Its successor, the Transiting Exoplanet Survey Satellite, or TESS, launched in 2018, is surveying nearly the entire sky, focusing on stars closer and brighter than Kepler's targets. In its first 2 years, TES identified more than 2,000 candidate exoplanets and confirmed at least several dozen, with many more awaiting follow-up observations. The numbers are staggering. As of early 2024, more than 5,500 exoplanets have been confirmed, and the statistical analyses suggest that planets are even more common than stars. On average, every star in the Milky Way has at least one planet. Many have several. Rocky planets in the habitable zone, the orbital band where temperatures allow liquid water to exist on the surface, are not rare. They are commonplace. Current estimates suggest that roughly 1 in 5 Sun-like stars has an Earth-sized planet in its habitable zone. In our galaxy alone, that translates to billions of potentially habitable worlds. Among the most intriguing systems discovered so far is TRAPPIST-1, an ultra-cool red dwarf star about 40 light-years from Earth, orbited by 7 planets, all of them close to Earth in size. At least 3 of these planets are in the habitable zone. The system is compact. All 7 planets orbit closer to their star than Mercury orbits our Sun, and the planets are likely tidally locked, with one face permanently illuminated and the other in perpetual darkness. Whether any of them have atmospheres, and what those atmospheres might contain, are questions that the James Webb Space Telescope is now beginning to answer. Another notable discovery came from the HARP spectrograph at the ESO's 3.6-meter telescope at La Silla, Gliese 6667 cc, a super-Earth about 5 times the mass of our planet, orbiting a red dwarf, roughly 24 light-years away, squarely in the habitable zone. The uncertainties are large. We know very little about the planet's atmosphere, surface conditions, or composition, but its existence demonstrates that rocky planets in habitable zones are not confined to Sun-like stars. They orbit red dwarfs too, and red dwarfs are by far the most common type of star in the galaxy. There have been surprises that no one anticipated. In 2012, a French team discovered a rogue planet, a world with no star, drifting alone through interstellar space, detectable only by its faint infrared emission. It was several times the mass of Jupiter. How it came to be unmoored from any stellar system is unknown. Perhaps it was ejected by a gravitational interaction with another planet. Perhaps it formed independently, condensing from a gas cloud too small to ignite nuclear fusion. Whatever its origin, its existence raised the unsettling possibility that the galaxy is full of dark, unseen worlds wandering between the stars. The search for exoplanets is driven by a question so fundamental that it borders on the philosophical. Are we alone? The discovery of life elsewhere in the universe, even microbial life, even the chemical traces of life long extinct, would be among the most profound events in human history. It would tell us that the emergence of life is not a cosmic accident, but a cosmic inevitability, that wherever the conditions are right, the chemistry of life finds a way. And if life is common, the probability that some fraction of it evolves intelligence and technology increases correspondingly. But the question of life elsewhere connects to a different question, one that is closer to home and more urgent, the question of our own planet's habitability, and whether we are in the process of undermining it. The Earth is, as far as we know, the only planet in the universe that harbors life. This statement may not remain true forever. The search for biosignatures on exoplanets in the atmospheres of Venus or Mars, in the subsurface oceans of Europa and Enceladus, is intensifying every year. But for now, it is a fact. We are it, and the conditions that make Earth habitable are not guaranteed. They are the product of a long, intricate, and surprisingly fragile chain of circumstances, any link of which, if broken, could render the planet uninhabitable. Our solar system formed approximately 4.6 billion years ago from a collapsing cloud of gas and dust, a protoplanetary disk not unlike the ones we can now observe in the Orion Nebula, where the Hubble Space Telescope has captured hundreds of young stars still surrounded by their natal disks. As the cloud contracted, small grains of dust began sticking together, forming progressively larger clumps called planetesimals. The larger a clump became, the stronger its gravitational pull and the faster it swept up surrounding material. Jupiter, the largest planet, was the first to fully coalesce, clearing its orbital path and dominating the dynamics of the early solar system. Its immense gravity shaped the architecture of everything around it, deflecting asteroids, capturing moons, and probably preventing the formation of a planet in what is now the asteroid belt. The early solar system was a violent place. In the inner regions, perhaps 20 small protoplanets jostled for orbital space, colliding, merging, shattering, and reforming over millions of years. From this chaos, 4 survived: Mercury, Venus, Earth, and Mars. The Moon, according to the current best model, formed from the debris of a glancing collision between the proto-Earth and a Mars-sized body called Theia. The impact was so energetic that it partially melted both objects, ejecting a vast cloud of molten rock into orbit around the Earth, which gradually coalesced into the Moon. This collision also donated much of Theia's iron core to the Earth, which is why our planet has a disproportionately large metallic core, and why the Moon, formed mainly from the lighter mantle material of both bodies, has a much lower density. The consequences of this accident were profound. Earth's large iron core, combined with the planet's rotation, generates a powerful magnetic field, the magnetosphere, that extends tens of thousands of kilometers into space. The magnetosphere deflects the solar wind, the stream of charged particles that flows continuously from the Sun at speeds of 400 to 800 kilometers per second. Without this magnetic shield, the solar wind would gradually strip away Earth's atmosphere, as it has stripped away most of the atmosphere of Mars, which lost its global magnetic field billions of years ago. Earth's atmosphere, in turn, is what makes the planet habitable. It traps heat, distributes energy from the equator to the poles, provides the oxygen that complex life requires, and blocks lethal ultraviolet radiation from the Sun. The Moon itself plays a critical stabilizing role. Earth's rotational axis is tilted at about 23.4 degrees relative to its orbital plane, and it is this tilt that produces the seasons. Without the Moon's gravitational influence, the tilt would vary chaotically over millions of years, swinging by as much as 85 degrees. At extreme tilts, the poles would point nearly at the Sun during parts of the orbit, producing climate swings so violent that complex life would be essentially impossible. The Moon acts as a gravitational anchor, keeping the tilt stable to within about 1 degree over millions of years. Without the Moon, there might be no civilization to wonder about its origin. Earth's position in the solar system is another piece of the puzzle. It orbits at a distance where water can exist in all 3 phases: solid, liquid, and gas. A few percent closer to the Sun and the oceans would evaporate, a few percent farther and they would freeze. This is the habitable zone, sometimes called the Goldilocks zone, and Earth sits near its inner edge, for for the first 2 billion years after its formation, the Earth's atmosphere contained almost no free oxygen. The earliest life forms, anaerobic bacteria and archaea, thrived in this environment, but the complex multicellular life that would eventually produce intelligence was impossible without oxygen. The transformation came around 2.4 billion years ago in an event called the Great Oxidation Event. Photosynthetic cyanobacteria, simple organisms that use sunlight to convert carbon dioxide and water into organic compounds, releasing oxygen as a waste product, had been slowly pumping oxygen into the oceans and atmosphere for hundreds of millions of years. Eventually, the oxygen overwhelmed the chemical sinks that had been absorbing it, primarily dissolved iron, which oxidized to form the vast banded iron formations that are now mined in Western Australia, Brazil, and elsewhere, and began accumulating as free gas. The consequences were catastrophic for the existing biosphere. Oxygen is a powerful oxidizer, essentially a slow-burning poison for organisms not adapted to it. The Great Oxidation Event likely triggered a mass extinction of anaerobic life, while simultaneously opening the door for the evolution of aerobic organisms that could use oxygen for respiration, extracting far more energy from food than anaerobic metabolism allowed. Over the next 2 billion years, atmospheric oxygen levels rose and fell, but the overall trend was upward, enabling the evolution of progressively larger and more complex organisms. The Cambrian explosion about 540 million years ago saw the sudden appearance of most major animal phyla in the fossil record, an event that may have been triggered at least in part by a spike in atmospheric oxygen. The oxygen-rich atmosphere also had another effect. It produced the ozone layer. Ozone is a molecule consisting of 3 oxygen atoms, formed when ultraviolet radiation from the sun splits ordinary oxygen molecules in the upper atmosphere. The resulting ozone layer absorbs most of the sun's ultraviolet radiation, protecting the surface from the DNA-damaging effects that would otherwise make complex life on land impossible. The colonization of land by plants and animals, which began about 470 million years ago, was enabled by the ozone shield. This shield came under threat in the late 20th century in what became one of the defining environmental stories of the modern era. In 1974, a postdoctoral researcher named Mario Molina published a paper suggesting that a family of industrial chemicals called chlorofluorocarbons, widely used as refrigerants, aerosol propellants, and solvents, could catalytically destroy ozone in the stratosphere. Each chlorine atom released from a CFC molecule could destroy more than 100,000 ozone molecules before being deactivated. In the 1980s, scientists working in Antarctica confirmed the prediction. Satellite and ground-based measurements revealed a vast region of depleted ozone centered over the South Pole, where stratospheric conditions, extreme cold polar vortex winds, and ice crystal clouds concentrated the destructive chemistry. The ozone hole, as it became known, extended across an area larger than the Antarctic continent itself. The international response was swift and, by the standards of environmental diplomacy, remarkably effective. The Montreal Protocol, signed in 1987 and subsequently strengthened, imposed a global phase-out of CFC production. Every nation on Earth signed it. CFC concentrations in the atmosphere have been declining since the mid-1990s, and the ozone layer is slowly recovering, though it will not return to pre-industrial levels until roughly the middle of this century. The Montreal Protocol remains the most successful example of international cooperation on an environmental issue, a template that the world has struggled and largely failed to replicate for the far more complex challenge of climate change. The story of climate change begins with a measurement. In 1958, a young geochemist named Charles David Keeling, working for the Scripps Institution of Oceanography, began recording the concentration of carbon dioxide in the atmosphere at the Mauna Loa Observatory in Hawaii. He chose the location for its remoteness, far from cities, factories and forests that might produce local fluctuations, and for its altitude 3,397 meters above sea level, high enough to sample well-mixed air representative of the global atmosphere. Keeling's measurements revealed two things. The first was a seasonal oscillation, a gentle breathing up and down, reflecting the northern hemisphere's dominance of the planet's landmass and vegetation. In spring and summer, as forests and grasslands across North America, Europe and Asia burst into growth, they absorb carbon dioxide from the air through photosynthesis, and the global concentration drops. In autumn and winter, as leaves fall and decomposition releases stored carbon, the concentration rises again. The annual cycle amounts to about 6 parts per million, peak to trough. The second thing Keeling's measurements revealed was a trend, superimposed on the seasonal oscillation. The average concentration of atmospheric carbon dioxide was rising. In 1958, when Keeling started, it was about 315 parts per million. By 1970, it had reached 325. By 1990, 355. By 2024, it had surpassed 425 parts per million, a level not seen on Earth for at least 800,000 years, and probably not for several million. How do we know what atmospheric carbon dioxide levels were 800,000 years ago? The answer comes from ice cores, long cylinders of ice drilled from the Antarctic and Greenland ice sheets. Snow that falls on these ice sheets is gradually compressed into solid ice by the weight of subsequent snowfalls, trapping tiny bubbles of air between the crystals. These bubbles are time capsules, samples of the atmosphere from the moment the snow fell, preserved in cold storage for millennia. By drilling deep into the ice, the deepest Antarctic cores extend more than 3,000 meters below the surface. Scientists can extract air samples dating back 800,000 years and analyze their composition. The ice core record reveals a pattern of remarkable regularity. Over the past 800,000 years, carbon dioxide levels have oscillated between about 180 parts per million during glacial periods and about 280 parts per million during warm interglacials. These fluctuations are driven primarily by periodic changes in the Earth's orbit, the so-called Milankovitch cycles, variations in orbital eccentricity, axial tilt, and the precession of the equinoxes that alter the amount and distribution of sunlight reaching the planet. The orbital changes are small, but they are enough to trigger feedback loops, changes in ice cover, ocean circulation, vegetation and atmospheric composition, that amplify the initial nudge into a full-blown glacial cycle. The current level of atmospheric carbon dioxide, above 425 parts per million, is not just higher than anything in the ice core record. It is rising at a rate that has no precedent in the geological record. The concentration is increasing by about 2.5 parts per million per year, and the rate itself is accelerating. The cause is not mysterious. It is the burning of fossil fuels, coal, oil, and natural gas, which releases carbon that was sequestered underground over hundreds of millions of years. Deforestation, cement production, and agriculture contribute as well, but fossil fuel combustion is the dominant source. The physics of what happens when you increase the concentration of carbon dioxide in the atmosphere was understood in the 19th century. Carbon dioxide is transparent to visible light but absorbs infrared radiation, heat. Sunlight passes through the atmosphere and warms the Earth's surface. The surface radiates heat back towards space as infrared radiation. Carbon dioxide in the atmosphere intercepts some of this outgoing radiation and re-emits it in all directions, including back toward the surface. The more carbon dioxide in the atmosphere, the more heat is retained. This is the greenhouse effect, and without it, the Earth's average surface temperature would be about -18 degrees Celsius instead of the current +15 degrees. The greenhouse effect is not a hypothesis, it is measured physics. What is debated, or was debated, before the evidence became overwhelming, is the magnitude of the warming produced by a given increase in carbon dioxide and the consequences of that warming for human civilization and the natural world, those consequences are now becoming visible. 16 of the 17 hottest years in the instrumental temperature record have occurred since the year 2000. Global average temperatures have risen by approximately 1.2 degrees Celsius since the pre-industrial era. This number sounds small. It is not small. The difference in global average temperature between the present climate and the depth of the last ice age, when ice sheets 2 kilometers thick covered much of North America and Northern Europe, is only about 5 degrees Celsius. A change of 1.2 degrees in a little over a century is, in geological terms, explosively fast. The polar ice sheets are responding. NASA's GRACE satellites, twin spacecraft that measure changes in the Earth's gravitational field with extraordinary precision, detecting variations caused by the movement of water and ice, have documented accelerating ice loss from both Greenland and Antarctica. From 2002 to 20, Greenland lost an average of about 280 billion tons of ice per year. Antarctica lost about 150 billion tons per year. The meltwater flows into the oceans, raising sea levels. From 1993 to 2023, global mean sea level rose by approximately 10 centimeters, and the rate of rise is accelerating. Satellite altimetry, precision radar measurements from orbit, shows that the rise is not uniform. Some regions, particularly in the Western Pacific and along the Atlantic coast of North America, are experiencing sea level rise 2 to 3 times the global average, driven by changes in ocean circulation patterns and the redistribution of water mass. The oceans have absorbed more than 90% of the excess heat trapped by greenhouse gases. Data from the Argo network, a fleet of nearly 4,000 autonomous profiling floats deployed throughout the world's oceans, shows that the upper 2,000 meters of the ocean have warmed by an average of about 0.09 degrees Celsius per decade since the mid-20th century. This thermal energy drives stronger hurricanes and typhoons, alters precipitation patterns, and disrupts marine ecosystems. Coral reefs, which support roughly a quarter of all marine species, are experiencing mass bleaching events with increasing frequency as water temperatures exceed the narrow range that coral can tolerate. The Earth observation infrastructure that monitors these changes is itself a product of the space age. Since the launch of TIROS-1, the first weather satellite in 1960, humanity has built a global monitoring system of extraordinary sophistication. Dozens of operational satellites in orbits ranging from low Earth polar tracks to geosynchronous positions 35,786 kilometers above the equator continuously measure atmospheric temperature and humidity profiles, ocean surface temperatures and currents, ice sheet extent and thickness, vegetation cover, soil moisture, atmospheric chemistry, and dozens of other parameters. The European Space Agency's Copernicus program, with its fleet of Sentinel satellites, represents the most comprehensive Earth observation system ever deployed, providing free, open access data to researchers, governments, and businesses worldwide. The data these satellites collect is voluminous, continuous, and increasingly urgent. But the story of space-based Earth observation began not with environmental monitoring, but with weather forecasting, and its evolution mirrors the broader trajectory of humanity's relationship with its home planet, from casual curiosity to dawning awareness to urgent alarm. The early weather satellites transmitted their images on analog systems. The Nimbus series, which began in 1964 and eventually included 7 spacecraft, carried increasingly sophisticated sensors that measured not just cloud patterns but atmospheric composition, sea surface temperature, and the extent of polar ice. All the data was recorded on 70mm film. No one thought to establish a long-term archive. The film was processed, the images were analyzed, and in many cases the original recordings were lost or destroyed. It was only decades later, when climate scientists began searching for historical baselines against which to measure current changes, that the value of those early records was fully appreciated. The irony is bitter. At the very moment when humanity first gained the ability to see its planet as a whole, to observe the interconnected systems of atmosphere, ocean, ice and biosphere that maintain the conditions for life, it was simultaneously and unknowingly disrupting those systems at an unprecedented rate. The carbon dioxide that Keeling measured at Mauna Loa in 1958 was already elevated above pre-industrial levels, and it has been climbing ever since. The ice that the Nimbus satellites observed in the 1960s and 1970s was already beginning its long retreat. The coral reefs that oceanographers mapped in the 1980s were already starting to bleach. The signals were there in the data, waiting to be read, but reading them required a perspective that only time and cumulative evidence could provide. The European Space Agency's Copernicus Atmosphere Monitoring Service now tracks the global distribution and concentration of carbon dioxide and other greenhouse gases in near real time, producing visualizations that show the seasonal pulse of CO2 as the northern hemisphere breathes in and out, the plumes of carbon monoxide rising from tropical forest fires in Africa and South America, the steady upward ratchet of the Keeling Curve. The data is unambiguous, the trend is clear. The question is no longer whether human activity is altering the Earth's climate. The question is how much, how fast, and what we are going to do about it. The International Space Station, orbiting 400 kilometers above the surface, provides a different kind of perspective, not instrumental, but visceral. Every astronaut who has looked down at the Earth from orbit reports the same experience. The atmosphere is thin, shockingly, terrifyingly thin. From the surface, the sky seems vast and limitless, an ocean of air stretching forever upward. From orbit it appears as it truly is, a paper-thin film of gas clinging to the surface of a rocky ball, so delicate that it seems impossible it could sustain anything, let alone the teeming complexity of the biosphere. This perspective, sometimes called the overview effect, has not unfortunately translated into the kind of urgent, coordinated, global action that the situation demands. The 2015 Paris Agreement set a target of limiting warming to 1.5 degrees Celsius above pre-industrial levels, but current national commitments, even if fully implemented, would result in warming of approximately 2.5 to 3 degrees by 2100. Recent climate summits have produced incremental progress, but no breakthrough. The gap between what is being done and what needs to be done remains large, and it is growing. While Earth observation satellites track the health of our home planet, a different fleet of spacecraft enables the communication systems that modern civilization depends on. The story of space-based communications begins, like so many stories in the space age, with a beep. On October 4, 1957, the Soviet Union launched Sputnik 1, the first artificial satellite. It was a polished aluminum sphere, 58 centimeters in diameter, with 4 trailing whip antennas. Its only payload was 2 radio transmitters broadcasting a continuous series of beeps at 20.5 and 40.02 megahertz. The signal was simple enough for amateur radio operators around the world to detect with homemade equipment. Few of them realized that the beeps were not random. They varied in duration and spacing according to the temperature and pressure inside the sphere, making Sputnik not just a propaganda triumph, but a genuine, if primitive, scientific instrument. Within 5 years, the technology had leaped forward. In 1960, NASA launched Project Echo, a 30-meter inflatable balloon of aluminized mylar, placed in orbit to serve as a passive reflector for radio signals. A phone call from President Eisenhower was bounced off the balloon from Washington to California. In 1962, AT&T built and launched Telstar, the first active communications relay satellite, capable of receiving a signal, amplifying it, and retransmitting it. The first transatlantic TV broadcast via Telstar carried a baseball game to Europe, followed by a press conference with President Kennedy, followed by a performance by the French singer Yves Montand. It was a charming, slightly absurd introduction to the satellite age. Telstar's life was cut short by an unexpected consequence of the Cold War. Both the United States and the Soviet Union had been detonating nuclear weapons in space above the atmosphere to test their effects on communications and missile defense systems. The tests generated intense pulses of electromagnetic radiation that created artificial radiation belts around the Earth. These belts damaged the electronics of several satellites, including Telstar, which failed within a few months. In October 1963, President Kennedy and Soviet Premier Khrushchev signed the Partial Test Ban Treaty, prohibiting nuclear tests in space, in the atmosphere, and underwater. The treaty was motivated less by environmental concern than by the pragmatic realization that both sides were destroying their own satellites. But it was, in retrospect, one of the more consequential arms control agreements of the Cold War, protecting the orbital environment that would become essential to modern civilization. The breakthrough that made satellite communications commercially viable was the geosynchronous orbit, an orbit at an altitude of 35,786 kilometers, where the satellite's orbital period is exactly 24 hours, matching the Earth's rotation. From the ground, a satellite in geosynchronous orbit appears to hang motionless in the sky, eliminating the need for tracking antennas and making continuous, uninterrupted communication possible. The first geosynchronous communications satellite was Intelsat 1, also known as Early Bird, launched in 1965. It could handle 240 telephone calls or one television channel simultaneously. Today, more than 240 active satellites occupy geosynchronous orbit, providing telecommunications, television broadcasting, weather observation, and military communications. The satellite telecommunications industry generates revenues exceeding $2 trillion annually, but geosynchronous orbit has a fundamental limitation: distance. At 35,786 kilometers from the surface, the round-trip signal time is about 240 milliseconds, nearly a quarter of a second. For voice calls, this delay is barely noticeable. For video conferencing, it is mildly annoying. For financial trading, where fortunes are made and lost in milliseconds, it is unacceptable. And for interactive internet applications, gaming, real-time collaboration, video streaming, it degrades the user experience significantly. This is the problem that SpaceX's Starlink constellation is designed to solve. Instead of a few large satellites at geosynchronous altitude, Starlink will consist of thousands of small satellites in low Earth orbit, between 340 and 1,200 kilometers above the surface, where the round-trip signal time is 20 to 40 milliseconds, comparable to or better than terrestrial fiber optic connections. The satellites communicate with each other via laser crosslinks, forming a mesh network in orbit that can route data around the globe at nearly the speed of light without touching the ground until it reaches its destination. The first batch of 60 Starlink satellites was launched in May 2019. By early 2024, more than 5,000 were in orbit, with plans for a constellation of up to 42,000. Each satellite is mass-produced, flat-packed for efficient stacking within the Falcon 9 fairing, and equipped with a single solar panel, a phased array antenna for communication with the ground, and a Hall-effect thruster using krypton as propellant for orbital maneuvering. At the end of their operational life, estimated at 5 to 7 years, the satellites are designed to deorbit and burn up in the atmosphere, reducing the risk of long-term space debris. The astronomical community has raised serious concerns about the impact of large satellite constellations on ground-based observations. Even with efforts to reduce reflectivity, including sunshades and anti-reflective coatings, Starlink satellites leave bright streaks across long exposure images, contaminating data and potentially interfering with the detection of faint transient events like supernovae and near-Earth asteroids. The Large Synoptic Survey Telescope, now called the Vera C. Rubin Observatory, which is designed to survey the entire visible sky every few nights, has run simulations suggesting that during twilight hours, when many survey observations are made, a significant fraction of images will be affected by satellite trails. The tension between commercial satellite operations and astronomical research has no easy resolution. Both activities are legitimate and valuable. Both occupy the same physical space, the night sky, and their requirements are fundamentally in conflict. The issue will only intensify as competing constellations from OneWeb, Amazon's Project Kuiper, and other operators join Starlink in low Earth orbit. Communications at interplanetary distances present challenges of an entirely different order. When NASA's New Horizons probe encountered Pluto in July 2015, it was 4.7 billion kilometers from Earth. At that distance, radio signals traveling at the speed of light take 4.5 hours to make the one-way trip. There is no possibility of real-time communication. Every command sent to the spacecraft was composed, reviewed, simulated, and transmitted hours in advance, with the controllers unable to receive confirmation that the command had been executed until nearly 9 hours after they sent it. The data rate was agonizingly slow. At Pluto's distance, New Horizons could transmit at only about 2 kilobits per second, roughly 1,000th, the speed of a basic home internet connection. The spacecraft collected about 50 gigabits of data during its brief flyby, and it took 16 months to downlink all of it. Only the 70-meter dishes of NASA's Deep Space Network, the 3 giant antenna complexes at Goldstone, California, Madrid, Spain, and Canberra, Australia, spaced roughly 120 degrees apart in longitude, so that at least one is always facing any given point in the sky, were sensitive enough to detect the signal. New Horizons kept going. In January 2019, it flew past Arakoth, a small Kuiper Belt object 6.6 billion kilometers from Earth. At that distance, the one-way light time was 6 hours and 7 minutes, and the data rate had dropped to 500 bits per second. The data from that encounter is still trickling in. Voyager 1, launched in 1977, is the most distant human-made object. As of early 2024, it is more than 24 billion kilometers from Earth in interstellar space, beyond the influence of the solar wind, traveling through the thin gas and dust between the stars. Its transmitter operates at 23 watts, about the power of a refrigerator light bulb. The signal that reaches Earth is so faint that the power received by the Deep Space Network's 70-meter dishes is about 10 to the minus 16 watts, roughly 20 billion times weaker than the power required to operate a digital wristwatch. Yet the signal is still detectable, and Voyager 1 continues to transmit scientific data at a rate of 160 bits per second. Voyager 1's nuclear power source, a radioisotope thermoelectric generator fueled by plutonium-238, is slowly decaying. The power output drops by about 4 watts per year. By the late 2020s, there will not be enough power to operate any scientific instruments, and the spacecraft will fall silent. It will continue on its trajectory, inert and unmonitored, for tens of thousands of years. In about 40,000 years, it will pass within 1.6 light-years of the star Gliese 445 in the constellation Camelopardalis. By then, the spacecraft will be long dead, a cold, dark artifact, drifting silently through interstellar space, carrying a golden record engraved with sounds and images of Earth. The golden record was Carl Sagan's idea. It contains 115 images, greetings in 55 languages, a 12-minute montage of sounds from Earth, including wind, rain, surf, birdsong, and whale calls, and 90 minutes of music from Bach to Chuck Berry. On its cover, etched in a language of scientific symbols, are instructions for playing the record and a map showing the Sun's position relative to 14 pulsars, rapidly rotating neutron stars, whose precise periods serve as a kind of cosmic GPS. If anyone ever finds Voyager 1, the map will tell them where it came from. The record will tell them who sent it. No one expects anyone to find it. The galaxy is too large, the spaces between stars too vast, but the gesture is significant. It says something about the species that made it, that we thought it was worth doing, even knowing it would almost certainly never be received. that we wanted to introduce ourselves to the universe, even if the universe was not listening. The sun, which powers all of this, every telescope, every satellite, every living cell on every planet is itself a subject of intense scientific investigation, because it is both the source of our existence and a potential threat to it. On September 1st, 1859, the British astronomer Richard Carrington was sketching sunspots when he observed something extraordinary. Two brilliant points of white light erupted from the sunspot group, flared intensely for about 5 minutes and then faded. Less than 18 hours later, auroras, the northern and southern lights, normally confined to high latitudes, were visible as far south as the Caribbean. Telegraph systems across Europe and North America went haywire. Operators received electric shocks. Some equipment caught fire. In other cases, telegraph lines worked perfectly with their batteries disconnected, powered entirely by the electrical currents induced in the wires by the geomagnetic storm. This was the Carrington Event, and it remains the most powerful geomagnetic storm in recorded history. If a storm of comparable intensity struck today, the consequences would be catastrophic. Modern civilization depends on infrastructure that Carrington's contemporaries did not have. Power grids, communications satellites, GPS systems, internet connections, financial networks. A severe geomagnetic storm can induce currents in long conductors, power lines, pipelines, undersea cables, strong enough to damage transformers and disrupt electricity supply over entire continents. Estimates of the economic damage from a Carrington-class event range from $1 trillion to $10 trillion, with recovery times measured in months to years. Understanding and predicting solar activity, space weather, has therefore become a matter of practical urgency. The sun is monitored continuously by a fleet of spacecraft. The Solar and Heliospheric Observatory, or SOHO, launched in 1995, orbits at the first Lagrange point between the Earth and Sun, about 1.5 million kilometers sunward, providing an uninterrupted view of the solar disk and its corona. NASA's Solar Dynamics Observatory, launched in 2010, observes the Sun in multiple wavelengths from geosynchronous orbit, capturing images every 12 seconds with resolution sufficient to track individual solar flares and coronal mass ejections. The twin stereo spacecraft, launched in 2006, orbit the Sun at slightly different speeds, providing stereoscopic views that allow researchers to plot the three-dimensional trajectories of coronal mass ejections and determine whether they are heading toward Earth. The Sun is not a simple object. It is a roiling, dynamic, magnetically complex ball of plasma matter so hot that atoms are stripped of their electrons, creating a soup of ions and free electrons that is an excellent conductor of electricity. The Sun's rotation, faster at the equator, where it completes one turn every 25 days, than at the poles, where the period is 38 days, stretches and tangles its magnetic field lines into increasingly complex configurations. The field periodically relaxes and reorganizes, flipping its polarity every 11 years in what is known as the solar cycle. During solar maximum, when the field is at its most tangled, sunspots, flares, and coronal mass ejections are frequent and intense. During solar minimum, the Sun is relatively quiet. Sunspots are cooler regions of the solar surface, the photosphere, where intense magnetic flux inhibits convection, reducing the temperature from about 5,800 Kelvin to roughly 3,800 Kelvin. Despite being cooler than their surroundings, sunspots are still far hotter than any terrestrial environment. They appear dark only by contrast. Individual sunspots can be larger than the Earth. Solar flares are sudden, intense bursts of electromagnetic radiation, from radio waves to X-rays to gamma rays, released when twisted magnetic field lines in the solar atmosphere snap and reconnect. The energy released in a large solar flare can exceed 10 to the 25th joules, equivalent to billions of nuclear weapons detonated simultaneously. Coronal mass ejections are different. They are vast clouds of magnetized plasma, billions of tons of material, blasted from the sun's outer atmosphere at speeds of hundreds to thousands of kilometers per second. A CME that strikes the Earth's magnetosphere compresses it on the day side and stretches it on the night side, where the distorted magnetic field lines can snap and reconnect, channeling streams of energetic particles into the polar regions and producing the auroras. The mechanism by which the solar corona, the sun's outer atmosphere, reaches temperatures of more than 1,000,000 degrees Kelvin remains one of the great unsolved problems in solar physics. The photosphere, the visible surface, has a temperature of about 5,800 Kelvin. The chromosphere, just above it, is hotter, about 8,000 Kelvin. The transition region, a narrow band above the chromosphere, sees temperatures leap to more than 500,000 Kelvin, and the corona, extending millions of kilometers into space, reaches 1 to 3 million Kelvin. This is profoundly counterintuitive. It is as if the air around a campfire were 1,000 times hotter than the fire itself. Simple heat conduction cannot explain it. Some other mechanism, magnetic reconnection, wave dissipation, nanoflares, must be responsible, but despite decades of observation and modeling, no single explanation has won universal acceptance. In 2018, NASA launched the Parker Solar Probe, the first spacecraft designed to fly directly through the sun's corona. Named after Eugene Parker, the physicist who first predicted the existence of the solar wind in 1958, the probe is on a 7-year mission that will bring it progressively closer to the sun with each orbit, using gravitational assist from Venus to slow down and lower its perihelion. On its closest approaches, the Parker Solar Probe will pass within 6.2 million kilometers of the solar surface, well inside the corona, traveling at approximately 200 kilometers per second, or 720,000 kilometers per hour, making it the fastest human-made object in history. The thermal engineering challenges are extreme. At its closest approach, the sun-facing side of the probe's heat shield will reach approximately 1,400 degrees Celsius, hot enough to melt steel. Behind the shield, the spacecraft's electronics operate at room temperature. The shield is made of a carbon composite sandwich with a highly reflective alumina coating that reflects most of the incoming solar energy during close approaches. The probe is out of radio contact. The sun's own radio emissions overwhelm the spacecraft's transmitter and must operate autonomously, keeping its shield precisely oriented toward the sun using onboard sensors and reaction wheels. The first images from inside the corona, transmitted during the outbound leg of the probe's first orbit, revealed structures that had never been seen before, fine-grained streamer patterns, spatial features far smaller than anything visible from Earth or from more distant spacecraft. The Parker Solar Probe is expected to operate through at least 2025 and possibly longer, providing the first in-situ measurements of the magnetic fields, particle populations, and plasma waves in the region where the solar wind is born and accelerated to its final speed. Meanwhile, the human ambition to extend our physical presence beyond low Earth orbit is gathering momentum after decades of dormancy. NASA's Artemis program, named after Apollo's twin sister in Greek mythology, aims to return astronauts to the Moon and eventually send them to Mars using the Space Launch System, the most powerful rocket ever built. The SLS draws heavily on Space Shuttle heritage. Its 4 RS-25 main engines are the same design that powered the shuttle's 3 main engines, and its 2 solid rocket boosters are 5-segment versions of the shuttle's 4-segment boosters. Each booster consumes 6 tons of propellant per second and provides more than 75% of the rocket's thrust during the first 2 minutes of flight. Unlike the shuttle's boosters, they are not recovered for reuse. The Orion spacecraft, which sits atop the SLS, is designed for deep space missions beyond low Earth orbit, beyond the reach of any crewed spacecraft since Apollo 17 in December 1972. It can support 4 astronauts for up to 21 days and is built to withstand the high-speed re-entry associated with lunar return trajectories. Its service module, provided by the European Space Agency, derived from the automated transfer vehicle that carried cargo to the ISS, supplies propulsion, power, thermal control, and life support. A 4-wing solar array generates 11 kilowatts of electricity, and the module's main engine is a modified version of the Space Shuttle's orbital maneuvering system. Artemis I, an uncrewed test flight, launched on November 16, 2022, sending an empty Orion capsule around the Moon and back over a 25-day mission. The flight was successful, demonstrating the SLS's performance and Orion's ability to withstand the thermal extremes of deep space and the 2,760 degrees Celsius heat of re-entry at lunar return velocity. Artemis II, planned for late 2025, will carry 4 astronauts on a similar trajectory, a lunar flyby without landing, the first crewed flight beyond low Earth orbit in more than half a century. Artemis III, which will include a landing near the lunar South Pole using a SpaceX Starship-derived lander, is targeted for 2026 or later. The lunar South Pole is of particular scientific and practical interest because permanently shadowed craters in that region contain water ice, confirmed by multiple orbital measurements and by the deliberate crash of NASA's Alcross probe into the crater Cabeus in 2009, which detected significant quantities of water vapor in the ejected plume. Water ice at the lunar poles could be extracted and processed into drinking water, breathable oxygen and rocket propellant, hydrogen and oxygen, potentially enabling a sustained human presence on the Moon without the prohibitive cost of launching all supplies from Earth. The commercial space sector, meanwhile, has transformed the economics and pace of space access in ways that would have been unimaginable 2 decades ago. SpaceX's development of reusable rocket boosters, first stage recovery is now routine, with individual boosters flying 15 or more times, has reduced the cost of launching a kilogram to low Earth orbit from roughly $54,000 on the Space Shuttle to approximately $20,000 on the Falcon 9. The company's Falcon Heavy, currently the most powerful operational rocket, can deliver 64 metric tons to low Earth orbit. And the Starship system, still in active development, is designed to be fully reusable and capable of delivering more than 100 metric tons to orbit at a target cost of less than $100 per kilogram, a reduction of more than 2 orders of magnitude from pre-SpaceX prices. Boeing's Starliner capsule, designed to carry astronauts to the International Space Station, has had a troubled development. Its first uncrewed test flight in December 2019 suffered a software error that prevented the spacecraft from reaching the correct orbit. A second uncrewed test in May 2022 was successful, and the first crewed flight took place in June 2024, though technical issues with the spacecraft's thrusters required an extended stay at the ISS. The two-way competition between SpaceX's Crew Dragon and Boeing's Starliner gives NASA what it calls dissimilar redundancy, 2 completely different spacecraft capable of the same mission, so that a failure in one system does not ground the entire crewed spaceflight program, as happened twice during the Space Shuttle era. The Sierra Nevada Corporation's Dream Chaser, a lifting body spaceplane designed to launch atop a conventional rocket and return to a runway landing, has a cargo contract for ISS resupply missions and is developing a crew-capable variant. Virgin Galactic has begun commercial suborbital spaceflights, carrying paying customers to altitudes above 80 kilometers for a few minutes of weightlessness and a view of the Earth's curvature against the blackness of space. These developments are unfolding against the backdrop of a fundamental shift in the relationship between government and private enterprise in space. For the first half-century of the space age, spaceflight was essentially a government monopoly, funded by taxpayers, managed by national agencies, driven by geopolitical competition. The government defined the mission, designed the hardware, hired the contractors, and assumed all the risk. The result was extraordinary capability at extraordinary cost, with little pressure to reduce either. The shift began in the 2000s when NASA facing the retirement of the Space Shuttle and the need to continue servicing the International Space Station, adopted a new approach. Instead of specifying every detail of the hardware and managing the design process, the agency would define performance requirements and let private companies compete to meet them, using their own designs, their own manufacturing processes, and their own money. NASA would be a customer, not a project manager. The risk would be shared, and the companies would retain ownership of their designs, free to sell launch services to other customers. This approach, sometimes called commercial crew, sometimes public-private partnership, produced SpaceX's Crew Dragon and Boeing's Starliner. Its success, particularly on the SpaceX side, has been so dramatic that it has become a model for how NASA intends to conduct future exploration. The Artemis lunar lander, for instance, is not being designed and built by NASA. It is being provided by SpaceX under a contract that pays for milestones rather than managing day-to-day development. The approach is faster, cheaper, and more innovative than traditional government procurement, though it carries its own risks, including the risk that a single company's technical or financial failure could derail an entire program. The International Space Station itself, the largest and most expensive structure ever built in space, assembled over more than a decade from components launched by the United States, Russia, Europe, Japan, and Canada, is approaching the end of its operational life. Current plans call for it to be deorbited in 2031, with a controlled re-entry over the South Pacific. Its successor is not yet defined, though several commercial companies, including Axiom Space and Orbital Reef, are developing private space stations that are expected to begin operations before the ISS is retired. There is a thread that connects all of these stories: the black hole at the center of M87, the exoplanets of TRAPPIST-1, the ice cores of Antarctica, the Parker Solar Probe diving into the Sun's corona, the Starlink satellites streaming across the dawn sky, the Orion capsule circling the Moon. The thread is this: we are a species that looks. We build instruments to extend our senses: telescopes, spectrographs, magnetometers, radar altimeters, photomultiplier tubes, and we point them at the universe and record what we find. We do this not because it is easy, not because it is profitable, not because it is safe, but because we cannot help it. The impulse to explore, to investigate, to understand is as fundamental to our nature as the impulse to breathe. And what we are learning through all these instruments and all these missions and all these decades of painstaking observation is both humbling and thrilling. We are learning that the universe is far stranger, far more complex, far more beautiful, and far more dangerous than we imagined. We are learning that our planet is a rare and precious thing, a fragile island of habitability in a cosmos that is, for the most part, lethal to life as we know it. We are learning that the conditions that sustain us are not permanent, that they can be altered, that we ourselves are altering them, and we are learning that the tools we have built to explore the universe are the same tools we need to understand and protect our home. The Hubble Space Telescope will not last forever. Its gyroscopes are failing one by one, and there will be no more servicing missions. Engineers have developed software workarounds that allow it to operate with fewer gyroscopes, currently 2 with 1 in reserve, but eventually the last one will fail, and the telescope will lose its ability to point with the precision that science demands. It will drift, uncontrolled, until its orbit decays and it re-enters the atmosphere, probably sometime in the late 2030s. By then, the James Webb Space Telescope will have been operating for more than a decade, and whatever comes after Webb will be on the drawing board or already in orbit. The extremely large telescope will open its eye in the Chilean desert. The Vera C. Rubin Observatory will begin its nightly survey of the entire visible sky. The square-kilometre array spread across South Africa and Australia will survey the radio sky with sensitivity and resolution that dwarf anything previously achieved. New gravitational wave observatories, successors to LIGO, perhaps including space-based interferometers like LISA, will detect the ripples in space-time produced by merging black holes and neutron stars, opening an entirely new channel of astronomical observation. Each of these instruments will expand our understanding of the universe. Each will produce discoveries that we cannot predict, because the history of astronomy teaches above all else that the most important discoveries are always the ones that nobody expected. The existence of dark energy, the accelerating expansion of the universe, was discovered by two teams of astronomers in 1998 who were trying to measure the deceleration of the expansion, who expected to find the opposite of what they found. The existence of exoplanets in bizarre, unexpected configurations, hot Jupiters, super-Earths, planets orbiting binary stars overturned decades of theoretical models about planetary formation. The cosmic microwave background radiation, the afterglow of the Big Bang, was discovered by accident by two engineers at Bell Labs who were trying to eliminate a persistent noise source in their radio antenna. The universe does not care about our expectations. It simply is what it is, and our job, our privilege, our burden, our delight is to observe it as carefully as we can and revise our understanding whenever the evidence demands it. This is the essence of science, not certainty, but the systematic pursuit of less uncertainty, not answers but better questions. There are questions being asked right now, at this moment, by researchers at observatories and laboratories and universities around the world, that may reshape our understanding of reality as profoundly as Copernicus or Darwin or Einstein reshaped it in their time. What is dark matter? What is dark energy? How did the first galaxies form? Is there life beyond Earth? What happened before the Big Bang? What is the nature of consciousness? Are we alone? These questions are not rhetorical. They are not abstract. They are research programs with budgets and timelines and teams of dedicated scientists working to answer them. The answers may come tomorrow or next year or a century from now or never, but the asking is what matters. The asking is what makes us human. The asking is what built every telescope, launched every probe, decoded every signal, and mapped every star. And so the search goes on in the frozen valleys of Siberia. Photomultiplier tubes watch the sky for flashes that might be natural or might be something else entirely. In the high deserts of Chile, segmented mirrors track the light of distant stars, searching for the tiny wobble or the brief dimming that betrays the presence of an unseen world. In laboratories in California and Texas, physicists design instruments that will fly closer to the sun than anything has ever flown, measuring the magnetic fields and particle streams that shape the space weather. Our civilization must learn to predict and survive. In clean rooms in Maryland and French Guiana, engineers test the components of telescopes that will look deeper into the infrared than any instrument in history, searching for the light of the first stars, the chemical fingerprints of alien atmospheres, the faint traces of a universe that existed long before we were here to wonder about it. The night sky from a sufficiently dark and clear location is one of the most beautiful things a human being can experience. The Milky Way, our galaxy, our home, our 400 billion stars, stretches across the darkness like a luminous river, and within it, invisible to the naked eye, but revealed by our instruments, are worlds beyond counting, phenomena beyond imagining, and mysteries beyond number. We have been looking up for as long as we have been human. We will continue looking up for as long as we exist. And every time we build a better instrument, every time we push our reach a little further, every time we find something we did not expect and are forced to rethink what we thought we knew, every time the universe reveals itself to be larger, stranger, and more wonderful than we had imagined. The light from the most distant galaxies Hubble has ever photographed left its source more than 13 billion years ago, when the universe was less than 500 million years old. It has been traveling through the expanding void for almost the entire history of the cosmos, crossing billions of light years of empty space, passing through the gravitational fields of galaxy clusters, being stretched and reddened by the expansion of space-time itself. And after all that, after 13 billion years of silent travel through the dark, it fell on a mirror 2.4 meters across, orbiting a small rocky planet around an unremarkable star in the suburbs of an ordinary spiral galaxy, and someone looked at it and understood what it was and was moved. That is what we do. That is who we are. We are the species that looks up.